Hello and welcome. My name is Elhelw. In the last video, I started talking about columnar databases or column stores, and I compared them or contrasted them with the traditional row-oriented databases in the sense of how the data is stored in each of them, as well as what types of queries are better to run on either of those kinds of databases. To summarize what we talked about last time, we started from the relational model saying that data is usually represented as tables with rows and columns and so on. In columnar databases or column stores, they're both the same meaning. In those kinds of databases, the data is stored column by column. So all the data, for example, in the ID column would be stored together. All the data in the first name column would be stored together. All the data in the last name would be stored together, and so on. This is different from what traditional row-oriented databases would do. So how does that look like on disk? Again, we mentioned that since the data is stored in pages, so we would have one page, for example, or more than one page that would have all the ID values. And then all the first name values would be stored together in one or more pages, followed by all the last name values, and then all the other columns. So for each column, all the values in this column would be stored consecutively within one or more pages, depending on the size of the data and so on. Storing the data in this way means that we only need to read the columns that we are interested in a given query. A given query usually targets a bunch of different columns. Of course, we're talking about queries that are more like analytical queries that have things like aggregation over whole columns and so on with lots of different rows. So for a query like that, it's easy to read only the columns that we need and not have to read the columns that we don't need or that are not referenced in the query. Of course, the main reason we want to do this is that we want to minimize the amount of I/O, the amount of data that we read from disk to memory in order to answer the query. So if we are able to read only, let's say, 2 or 3 columns or however number of columns that we're referencing in the query and ignore the rest, then this saves a lot of I/O costs. The thing that I'm going to talk about today is another way to reduce the I/O cost even further, and that's using data compression in columnar databases. When we use data compression, it means that a given amount of data, we want to compress that so that it occupies less storage space. When we do that, of course, we save the storage space, which is great, but more importantly, we save the I/O cost required to read that data from disk to memory. When the data occupies a smaller space on storage, then when we read that into memory, we're going to use less I/O, assuming that it occupies fewer number of pages, of course. If the data still happens to be within the same number of pages, then the amount of I/O is going to be the same. So compression usually means that the data becomes smaller, so it occupies fewer pages, so the I/O cost becomes a lot less. When we're talking about compression in the context of databases specifically, we have to talk about lossless compression. We need a way of compression that does not lose any information, meaning that when we compress the data, now it's compressed in a smaller form, we have to be able to decompress it or extract it into its original form again, while guaranteeing that that extracted data is basically the same as the original. There are no changes, there are no lost information there. When you talk about compression in general, it can either be lossy or lossless, right? Lossy means that when you compress and then decompress the data, the result of that is not exactly the same as the original. An example for those who are familiar with image processing, for example, when you talk about JPEG compression. JPEG images are a compressed form of images. So basically it takes the original, it runs some compression algorithm, it produces an image that is much smaller in size and approximately looks similar to the original, but this is a lossy compression. So it loses a little bit of the quality, a little bit of the resolution, right? So if you look at it from a very, so the resulting image may have some pixels that have been changed and so on to produce that smaller size. So it's not exactly the same as the original. For databases, you cannot do something like that. You have to have a lossless compression so that you guarantee that the data does not change. It would not make sense, for example, if you start with some product IDs, for example, and you want to compress those, and then when you decompress it, the IDs are different. Of course, that makes no sense. Or if you start with product quantities in a store and you compress that data, but then you decompress it and then the quantities are different. Of course, that also makes no sense. So you need to guarantee that the data does not change. So that's why we need a lossless compression. Another thing that I need to mention is that yes, we said that the main reason for compressing the data is to reduce the storage space and reduce the I/O costs. However, this is not free. Anything, again, has a compromise. When you reduce the I/O costs, you introduce another cost. The cost of compressing and decompressing the data, that's computation, that's CPU cost that we are introducing. The hope is that the I/O cost that we're saving is a lot higher than the overhead that we added for compressing and decompressing the data. All right. So this is the concept of compression in general. Why is this related specifically to columnar databases? Why are we talking about that in the context of columnar databases? The reason is compression is a lot more effective, and by effective I mean it helps to reduce the size of the data significantly. It's only effective when the data is similar to each other. You cannot really compress a lot of data when all the data is completely different from different domains, different values, and so on. When the data is similar, so like, it's in different domains, so like you're dealing, for example, with only integers or only dates or only, a set of values that has only 5 distinct values or something like that, it's a lot easier to compress a large amount of data that looks like this into a much, much smaller size. When you're talking about data that is very different, you have a date and a number and a string and an ID and all these different things, it's very hard or almost impossible to compress that significantly. So when we talk about row-oriented databases, the data looks like this. You have a full row, you store that together, and then you store the next row and so on. So for each row, the data is all over the place. Very different domains, very different values. You have like an ID followed by first name, followed by last name, so some 2 strings that are names, followed by a phone number, so that's a string but it has a format of a phone number, followed by a date, followed by another string that is a job title, and so on. So the data is very, very, very different from each other. It's extremely hard, even if it's even possible, to compress that. Of course, there are some tricks that you can do, like for example reducing any unused spaces and so on, but it's still very limited in terms of the capacity that you would save. When we talk about columnar databases, the data is stored as columns, right? So you have the ID column stored together, the first name, last name, and so on. Now, when we look at each of these columns by itself, the data is very similar to each other. All of the data is in the same domain. The values might be close to each other, or they might be, a limited set of values, and so on. So like the IDs are all integers, for example, the first names are all strings. You might see a lot of similarities in the first names. The phone numbers, they all have the same format. The higher dates will probably be within a very small range of dates for employees in a given department, for example. The job titles, again, you have a limited set of job titles to choose from. Same thing for departments. The salary range will also be somewhat of a small range, not that big. So the data is very similar within each column. So this means that you can do a lot of a better job compressing this information. So the workflow in general looks like this. You have a bunch of data that you have that you want to add to the database. So as you're loading this data into the database, you're also doing the compression. So you store, or the system ends up storing, the compressed form of that data. And like I said, this happens during the loading of the data into the database. Now, what we're storing is the compressed form of the data, right? So when we have a query that comes and we want to run this query on the data, we need to read that data from disk, the compressed data, and then do the processing. So in order to run the query on the compressed data, we first need to decompress or extract that data, right? One way to do this would be just like take the data, run the reverse algorithm of whatever we did during the compression, produce the original data again, and then run the query on that data and produce the output. That's kind of like the intuitive approach. This is usually not the best way to do it though. Think about that decompression step. We have data that is compressed and we want to transfer it back to its original form. First of all, think again about what is the use case for columnar databases. We're dealing with usually data warehouses that have analytical queries and so on. So the size of the data is pretty big. Each table by itself is usually pretty big. So if you want to decompress a whole table, the decompression cost is going to be huge. That's one. Secondly, where are you going to put the decompressed data? Assuming that we want to decompress it and put the result in memory so that we can run the query on it. Given the size of the data, it might not be possible to fit this in memory. So the system will end up having to spill some of that to disk, or be like, keep writing and reading from disk to memory to keep the pages that are being used in memory the whole time. So this basically means that we're introducing even more I/O here than we need to. It kind of defeats the purpose of the compression in the first place. So this is usually not the best way to run queries on compressed data. What systems usually try to do, as much as possible, of course, like you might still have to do this in some cases, but as much as possible, systems try to run the query directly on the compressed data. Maybe not the actual query that you want to run, but like a modified version of that might be able to run on the compressed data to produce some output. This output might not be the final output that you want to return to the user or to the application, so you might still want to decompress or do some transformation on that output to produce the actual query output that will be equivalent to the one from the first scenario. The good news here is that the amount of data that you want to do that decompression or transformation on is usually a lot less, because that's the result of the query. So query that does aggregation, for example, or filtering and so on, will end up producing a result set that is a lot smaller than the original data. So then when you try to decompress or transform that data, it's a lot cheaper, and it can be done in memory, in most cases at least. So basically what I'm trying to say is that when systems choose compression mechanisms or compression techniques, they want a technique that allows them to do that second path. When we're talking about compression techniques for columnar databases, the basic idea is that we want to be able to combine multiple values from the same column into a single value or into something smaller in size. There are multiple different techniques that do this. We're going to focus on two of the main techniques that are frequently used in many systems today, but there are a lot more than those two. The first technique we're going to talk about is called run length encoding, usually represented as RLE for short. Let's explain it with an example. So let's assume that we have a department column in the employees table, the same example that we've seen earlier. So all the values in that column are stored together, since again we're talking about columnar database. So we have things like engineering, HR again, because these are coming from different employee records, IT, and so on. So these are all the values in the department column, and we want to compress those using RLE. So for run length encoding, basically the technique works as follows. It collects all the consecutive repeated values and then combines them together, as we'll see. So starting from the beginning, we have engineering, and this is only once. It's not repeated consecutively. It might be somewhere else later on in the values, but at least there is no another engineering value right next to this one. So in the output, in the compressed data, this will be represented as the value plus the number of repetitions. So it's going to look like this, engineering and 1, because it's only encountered one time. Next, we have HR repeated 3 times in a row. So this will look like this, HR 3. Next, we have IT repeated 2 times, so we're going to put IT and 2. So basically each value, we put that value once, and then we put the number of repetitions next to it. So same thing, engineering 2, HR 1, IT 2. Of course, in the example here, it might not be super clear, but in reality, these values might be, first of all, a lot longer, not just 2 or 3 letters. And the repetitions will also be a lot more. So by reducing each group of repeated values to one value and an integer, of course, integers are also small compared to strings. Strings might be 30, 40, 50 bytes, 100 bytes, whatever it is. Integers could be 4 bytes, for example, right? So in this case, meaning that you reduce the size pretty significantly. Now, any compression algorithm has best case scenarios and worst case scenarios. The worst case scenario here, what would that be? The worst case scenario here is if there are no consecutive repetitions at all. Like you see engineering followed by HR, followed by IT, followed by engineering again, followed by IT again. So each value appears only once in a row. There's no consecutive repetitions. This means that the output will pretty much have the same values plus 1 after each value. So basically the size of the output is now greater than the size of the input data. So the compression actually backfired in this case. This is the worst case scenario. So if a system finds a column like that, it should not use RLE with it. Best case scenario is the opposite, is if the data is sorted, or if basically all the similar values are found together. So something like this. All the engineering values are together, all the HR values are together, all the IT values are together, because this means that you're going to encounter each of these values only once in the output. So the output is going to look like this: engineering 3, HR 4, IT 4. You're not going to see those again. So basically this is the minimum size that you can occupy for these values. If the data is sorted like this, great, RLE works very well. Or in some cases, we might have to, like the system might have to sort the data to put it in this way before it can apply, RLE on it. Of course, there are middle grounds which can also be good. Like the data doesn't have to be sorted for RLE to work well, but as long as you have large number of repetitions for every value that you encounter, like if you, let's say, found engineering 10 times, followed by HR 20 times, followed by engineering again 10 times, and so on, then this should be good enough to give you a good compression ratio. Now, let's assume that we have this compressed data, right, using RLE. We talked about queries. Can queries run directly on the compressed data? In some cases, yes, depending on the query, of course. If we have a query like this here, for example, that selects department and counts star, grouping by department, meaning that you want to output each department and the number of employees in that department, right? So if we have the data represented like this, we don't have to decompress it first. We can run this directly on the compressed data, because basically we have in the data here departments and number of rows that had that value. So basically for engineering, I will just have to add up, engineering 1, a little bit later there's engineering 2, so total means that engineering appears 3 times in the table, so this is the count star basically. So in something like this, you can run that directly on the compressed data. Of course, when I say you, I mean the database system. And for that to happen, the implementation of the aggregation algorithm needs to take into account that if the data looks like this, then it's a slightly different implementation from the original implementation that runs on the uncompressed data. So usually systems that support this kind of compression would have different implementations for the operations to be able to run on different formats of the data. The second compression technique that we're going to talk about is called dictionary encoding. Again, let's explain that with an example. Assuming that we have a table with products in them and each product has a color. So this is the color column. Have red, white, black, blue, etc., etc. And again, we want to be able to compress these values. So in this case, we're going to use dictionary encoding. Dictionary encoding says that the first thing we're going to do is that we're going to build this dictionary that has all the values that we can see in this column, and we're going to assign a code to each value. Code is usually, a numerical value, an integer, for example. So in this particular case, we have 4 distinct values: red, white, black, and blue. So we're going to give them these 4 codes. And then we're going to transform the original column into the compressed version by replacing each value with its corresponding code. So the compressed version will look like this. Again, we gain compression here because the original values might be, again, here in the example, they're strings. Strings can be pretty large, 20, 30 bytes and so on. And we're going to replace each of those with an integer value that can be, let's say, 4 bytes, right? So the data is compressed very significantly. And of course, we have to also store that dictionary with us. So that also counts as part of the compressed data in this case. Now, someone may ask, why do we even need to store the dictionary? Why not just use some function, for example, like a hash function, right? Like if you apply hash function on the values, that will give you an output value, and then you can just store that as the code, right? The only problem with that is that we cannot go back, cannot transform the hash value back to the original value. And we need that, because if we store the compressed data and we have a query on it that needs to produce the actual colors, in this case to to the output, then we need to be able to go back from the codes to the original values, and you cannot do that with hash functions. That's why we need to store that dictionary with us to be able to transform in both directions. Now, again, let's look at queries. So again, given this compressed data, some queries you might be able to run those directly on the compressed data without having to, change it. For example, if you have a query like this, let's start from products where color equals to blue. Now, in order to run this on the compressed data does not have blue or red or black or any of the actual colors, right? So in this case, we need to actually transform the query into something a little different. So basically the system would look at the dictionary, see that blue corresponds to the value 3, so it will transform the query to select star from products where color is equal to 3, and then you can run this on the compressed data directly, and then once we have the result of that query, then we can do the transformation back to get the actual colors, right? So this is what I mentioned earlier, that the transformation will then only apply on a smaller set of rows that satisfies this query and becomes a lot cheaper. So this is basically what dictionary encoding is. Like I mentioned, there are other compression techniques. You can look these up, things like bit packing, delta encoding, and others. But the two that we talked about today are the most frequently used in most systems. If we need to do another video on the other techniques, I can probably do that as well later. But again, the two that we talked about today are the most popular ones. So to summarize what we talked about today we continued our conversation about columnar databases or column stores. I focused today on compression as a way to reduce the data size and also reduce the I/O costs associated with reading data from disk. Compression is possible in columnar databases because the data that is stored together is very similar in terms of domain, in terms of values, and so on. So it's easier to achieve a lot higher compression on this data. We talked about two compression techniques, namely run length encoding and dictionary encoding. Run length encoding tries to combine all the repeated values that are occurring consecutively into a single value and a count. Dictionary encoding builds the dictionary using the original values and codes and then replaces each value with its code in the output in the compressed data. And like I said, there are other techniques that can also be used for the same effect. If you have any questions or comments, please let me know and I will try to answer them as soon as possible. If you found this video useful, please hit the like button. And if you're not subscribed already to the channel, please subscribe so that you can get the latest videos. Thank you so much for watching, and I will see you in the next video.